So today we are happy to have Valentino Tosatti driving all the way from New York City to tell us about special Kähler geometry and collapse.
Okay, thank you, Saman, for the introduction and for the kind invitation. It's of course great to be back in CMSA, where I spent a long time as a visitor at some point in the past years. So yeah, so I will talk about some not super recent work, but I thought it was connecting well with the physics, sort of about special Kähler geometry and connection with the collapsing theory, which is something I've been very interested in for a long time. So the papers are, in fact, all on arXiv and maybe even published. There's one with Mark Gross and Zhang Yuguang, and another one with Zhang Yuguang. And if I have time, I will mention also another one with Yang Li, but this is maybe there won't be time. So mostly it will be with these people here. So just in fact, it will be mostly kind of gentle introduction, and the main theorem or theorems will come later. So hopefully that's okay as a strategy. So the motivation and introduction is first to talk about special Kähler geometry. So again. So it originated in physics, so I'm of course a mathematician, so I don't really know about this, but it came from, I think it's d-dimensional and it was two supersymmetric gauge theories. Don't ask me more, but this was in the 80s, so quite a long time ago, and there were initially some physicists that I don't really know. Later, Strominger, Cyber-Witten worked on this more. And finally, the mathematical study was initiated in a famous paper by Dan Freed. So in 1999, and so I will, at least the basic introduction will draw from Dan's work. So the definition or setting is the following, and then the motivation will come after. So let's just first take it as a kind of abstract intrinsic definition. So special Kähler, so there should be a complex structure. So we'll have a complex manifold Mj. So J is the complex structure, and it's integrable, so it's covered by charts like Cn. So n will always denote the complex dimension. So the real dimension is 2n, and so this is the manifold, and I do not assume that it's compact necessarily. In fact, it will likely be non-compact, and so I need some geometry. So G will be a metric, and it should be Hermitian with respect to J, and also Kähler. So G will be a Kähler metric on this manifold. So that means that G is Hermitian, so G, and the two form, well, I don't know, let's put it here, is closed. So this two form satisfies d omega equal to 0. So this is the Kähler property. All right, so that's just a definition of a Kähler manifold. Oh yes, you made it, I think. Okay, I hope you're feeling okay. Fine. You're fine, okay. So I was saying it would be a pretty gentle introduction at the beginning. So, right, so what is a special Kähler? This is just the definition of a Kähler manifold. A special Kähler metric is, or special Kähler structure, on this Mj, let's say G, omega, whatever, put all together, is going to be nabla, which is a connection, so flat, torsion-free connection on the real tangent bundle. So let me just blur the difference between real and complex tangent bundles, but this should be the real one, such that it's a symplectic connection, so the symplectic form is parallel, and the crucial condition is that not that the complex structure is parallel, but that d nabla of the complex structure is 0, where d nabla is the usual skew-symmetrized operator. So for example, here it would go from one forms with value here into two forms with value in the tangent bundle. You obtain it by first applying the nabla and then skew-symmetrizing cotangent indices. So, and the J operator is an endomorphism of the tangent bundle, and you can think of it as a one form with values in Tm. So this is the special Kähler property. So this again was this definition was posed by Dan based on some non-intrinsic definitions from physics. This is very different from nabla J equal to 0. So nabla J equal to 0 will imply this, but this is weaker. So you don't assume that. And what can you get from this? So it's a bit mysterious, this connection. In general, this nabla is not the Levi-Civita connection of G, and it's not which is the same as the Chern connection of G, so it's a different connection. And what you can do, so what was realized is, first of all, from this, so because you have a symplectic form, you can locally find the Darboux coordinates, and you have this symplectic form is parallel, so you can find the parallel Darboux coordinates, and from those you can construct so-called special complex coordinates. So locally, you can always find some special holomorphic coordinates, complex coordinates, let's say Zi, let's put it up here, from 1 to n, and also a local holomorphic function f, so local holomorphic function, such that the Kähler form omega in these coordinates is given by the standard. This will be the flat Euclidean metric, and here you have the imaginary part of the Hessian of this f, Zi, Zj. So this, not the complex Hessian, but that would be 0, but the holomorphic Hessian of the Z. And from this, in particular, you see that this matrix here, which is sometimes called the Zij, oh, sorry, there's a clash of notation. Sorry, I said J and K, not I and J. So this matrix here, let's say JK, this Hessian, belongs to the Siegel upper half space. So it belongs to the Siegel upper half space, n-dimensional Siegel upper half space, Hn, of n by n complex matrices, which are symmetric, right? So this is clearly a symmetric matrix, and the imaginary part is positive definite. So imaginary part positive definite because it's the coefficient of the Kähler form in this holomorphic coordinates. So this is a first hint of some kind of period matrix that lies behind, but this is only purely local, and that's the proofs are all in Dan's paper, and you can also write the Kähler potential. I mean, this just writing down some basic geometry of these. So if you call, let's say, Zi star, one derivative of this f. So f has some name in physics, the holomorphic prepotential or something. So if you take just one derivative of the holomorphic prepotential, you get new holomorphic coordinates, I from 1 to n. These are some called conjugate local holomorphic coordinates. So these are also local holomorphic coordinates. And they have the property that if you take the real part of dzi, this is you can call it dyi, and the imaginary part of dzi star, you can call it maybe minus dyn plus I from 1 to n in this whole discussion. So these are actually parallel, and the yi gives you the usual real Darboux coordinates. So y1 up to y2n are Darboux coordinate in the sense of symplectic geometry. So the Kähler form is also written as dyi wedge dy n plus I in this chart. So there's basically there's a symplectic viewpoint of Darboux coordinates which interacts with this holomorphic world because of these two conditions, and you obtain this some kind of compatibility between the two. And if you have take two different such charts, the Darboux coordinates in one chart and in the other chart are related by an element in the symplectic group. So the change of charts, change of Darboux charts lie in this SP to NR. So they have to lie in the symplectic group. And furthermore, also, so maybe the last thing I will mention is the Riemannian metric G, which was earlier on this board, is in fact the Hessian of a function. So it's Hessian of phi in Darboux coordinate. So this is the real Hessian in these coordinates above, where phi as an explicit expression is maybe 1/2 the imaginary part of the sum of this Zi star Zi conjugate. So this would be the Kähler potential of omega. Kähler potential, I mean local Kähler potential. So omega is a dd bar phi, and the metric is actually the real Hessian of phi. So this appeared already in the work of Cheng and Yao, for example, earlier. And what Hitchin, I think Hitchin realized this part. And the determinant of this matrix is constant. So Hessian of phi is constant, some positive constant. So it's a solution of the real Monge-Ampère equation. So this all comes for free just from these assumptions here. So these metrics, which are in the local coordinates, are the real Hessian of a function and have constant determinant, again, appeared in the work of Cheng and Yao. They're called maybe Monge-Ampère metrics or something. So, okay, I think this is maybe all the basic local geometry. Maybe I can also mention that if you keep doing this game of taking holomorphic derivatives of f, so here there's one derivative, here there's two derivatives. You can also take three derivatives. You obtain a holomorphic cubic differential, which plays a big role in this story, but I think I probably don't need it too much right now. So if I need it, I will write it later, yes.
So there seems to be kind of a torus flavor here.
Yeah, it's coming soon. Yes. So yeah, right now there is no torus, but in 1 second there will be a torus. Basically, it will be assuming that these have values in Z, SP2 and Z. So that will come soon. So if you have that, then there will be a torus magically appearing. But yeah, otherwise, yes, you're right. There is not quite a torus. So yeah, I will explain in a sec. Yes. Some examples, I mean, it's not hard to write down examples of these metrics, especially in low dimensions. I mean, the kind of stupid example in CN would be to take this f, the kind of holomorphic parabola, you know, I over 2, I don't know, summation of Zi squared. So this kind of quadratic polynomial. If you do this, then you just get G, the flat Euclidean metric on Cn. So this is special Kähler. It's in somehow a not super interesting one. So the special Kähler metrics which happen to be flat are, I mean, locally isometric to this example, and they're less interesting. Okay, but still they are examples. And then you can write down many, many more. For example, I don't know, just write down one of them on the unit ball, puncture unit ball in C star, in C, whatever, in C star. So take the ball, but remove the origin. You can take, say, omega to be minus Z log Z, and then times the Euclidean 1. And it turns out that this is actually special Kähler. This is special Kähler. And you could write down all the other data for this one. And you can see that it has some kind of singularity at the origin. So if you try to fill it in, it's a singular metric at the origin. And many more examples can be written, especially in one complex variable. It's particularly easy to write. So, okay, this so far comes without motivation, so maybe we should discuss some geometry first. So, of course, the motivation came originally from physics. This thing came up in this structure came up in supersymmetry, as I mentioned at the very beginning. So geometry, so the special Kähler metrics have very, very rich geometry. I mean, they're indeed very special objects, as the name suggests. But if you find one, they have a hugely interesting geometry. So, for example, a basic calculation of that was that this G, assumed to be special Kählers now, right, has, in fact, non-negative curvature. So has non-negative so-called bisectional curvature. This is the strongest possible notion of curvature on a Kähler metric. So the strongest curvature you could think of basically is non-negative. So it's non-negatively curved. In particular, the Riemannian sectional curvatures are non-negative also, if you think about those. In fact, Freed has a formula for the Riemann curvature tensor, as it's basically a perfect square of this holomorphic symmetric cubic form, basically. So the cubic form has 3 indices. If you square it, you have 6 indices, so you need to contract 2, and then you have something with 4 indices, which is some kind of perfect square, and it's non-negative definite. So that's very, very nice. And Zhechin Lu, I think immediately after reading the preprint, noticed that if a special Kähler metric G is complete, in the sense of Riemannian geometry, defines a complete metric space, then it has to be flat. So then G is flat. So that's also interesting. So basically all the non-flat and therefore interesting special Kähler metrics will never be complete, like this one here. So this one here is complete, and it's indeed the non-interesting one. And that one is incomplete. So that's good. So we're going to study the metric completion also later. So when you have an incomplete metric space, you can perform a completion by adding equivalence classes of Cauchy sequences, and you get a complete metric space where your incomplete one embeds, and that we're going to study later. So it's going to take a little time to get there. So some bullet points. And a very interesting point, which again came from physics, and it was elucidated by, certainly in Dan's paper, but I think it was some, maybe Cecotti and some physicist friends discovered this in the physics context, namely that if you have a special Kähler manifold and take the cotangent bundle, so it's even if M was compact, this will be non-compact, this actually admits a hyperkähler structure, and in fact a so-called semi-flat hyperkähler structure, so I will discuss in a second. So, okay, assuming that M is special Kähler. So hyperkähler, just a quick refresher, it means that you can construct 3 complex structures, I, J, and K on this manifold. So strictly speaking, they're endomorphism of the tangent of the cotangent, right? And then they're integrable, and they satisfy the quaternionic relations, satisfy quaternions. So I composed J would be equal to K, and so forth. So of the usual identities from Hamilton quaternions. And also it admits H, let's call it Riemannian metric, not on M, but on T star M, so metric on this manifold, and which is Kähler with respect to all 3 complex structures. So Kähler and H is Kähler with respect to I, J, and K. So this is this hyperkähler notion. The name hyperkähler came from Calabi, and the interesting point is that if you call omega I, omega J, omega K, the 3 Kähler forms, constructed from this H and I, J, and K, then if you look at, say, big omega I, which is omega J plus the imaginary unit times omega K, this is actually a holomorphic symplectic 2 form with respect to I. So with respect to the complex structure I, you have a non-degenerate holomorphic 2 form. So that's the symplectic notion. And similarly, if you do some cyclic permutation, if you put here J, K, I, that's a holomorphic symplectic form for the J complex structure and so forth. So, and in fact, you can do also linear combinations. You can do AI plus BJ plus CK, where ABC are real numbers on the unit sphere, a squared plus b squared plus c squared equals 1, and you get a whole S2 of hyperkähler complex structures. So you get a whole S2 of complex structures, and H is scalar with respect to all of them. So this is this so-called twistor space of the hyperkähler manifold. And good. So that's, yeah, semi-flat. Semi-flat just means that when you restrict H to the vertical direction, so in this T star M there's a vertical direction, then it's precisely a flat metric on Cn, on the vertical direction. So, and this, okay, I'm not writing down the formula for H, but it's not terribly complicated. It's basically constructed from G. So the tangent bundle of this can be sort of canonically identified with Tm direct sum T star M, and you can use the metric G on both of them, basically. All right, and the symplectic form is also used to identify T star M with Tm if you want. All right, so, okay, this is one piece of geometric data, and now the interesting part, which relates to Michnia's question. So if you have a lattice in T star M, so by this I mean it should have a full rank, right? So lambda should be like z to the power 2n, right, with my notation, and you assume that it's flat, so nabla flat. So maybe it should be nabla dual, you know, the dual connection. So a lattice which is preserved by this nabla. Then, I mean, lattice subbundle, I meant to say. So on each fiber is a lattice. So it's a Z2N bundle, which is flat, and also such that the holomorphic symplectic form on the lattice is identically 0. So this is the Lagrangian condition, lattice Lagrangian. Then you can actually take the quotient. So if you take the cotangent bundle and you mod out by this lattice bundle, and you call it X, then this one here, X, is hyperkähler. It comes with a projection to pi. So this X here is hyperkähler. Because you are going to use the same hyperkähler structure you had here and prove that it's invariant by the action of the lattice. So it descends to a hyperkähler structure here. And now, indeed, the fibers are tori now. So with the fibers which are actually complex Lagrangian tori, and in fact there are abelian varieties. So complex Lagrangian just means this connotation here, the same thing. So there are Lagrangian abelian varieties. So secretly, the fact that you have this flat, integral structure here, subbundle, already implies that when you change from one of these flat Darboux coordinates to another one, the change of the linear part is in SP2 and Z. So now this implies that it's in the Z, in the integral lattice, and this is what gives you that the fibers are not just tori, but they're actually abelian varieties. This object is called an algebraic integrable system. So it's in some sense the holomorphic version of an integrable system in classical mechanics. So this is hyperkähler, and it's fibered by this abelian variety. So the picture is just naive picture. It's yes. Here nothing yet. Yes, it's completely submersion everywhere. Yes. So I will have them very soon. In fact, yes. So for now, it just looks like this. So some kind of fibration over M. So this is this X. Right. So the point is, yes, M could be compact. However, if M is compact, the Riemannian metric is automatically complete. And so by Zhuqin-Lu, it has to be flat. So yes, there is no inherent contradiction, but morally speaking, you should think that M is non-compact. Or else the base is basically a torus itself, or a finite quotient of a torus. Yeah. But yes, soon enough, I'm going to allow singular fibers, but for now, they're not there. And there's also a converse. So conversely, if you have a hyperkähler, so I'm not saying compact yet. So if X is hyperkähler, so really I should say X, I, J, K, H, whatever, all the data. And if I have a pi from X to M, so M is a complex manifold, and assume that this is a holomorphic, indeed, complex Lagrangian torus fibration. So Lagrangian with respect to the holomorphic symplectic form that you have on the hyperkähler, this big omega, Lagrangian torus fibration. So Lagrangian torus fibration. I mean, since it's Lagrangian, the dimension of the torus must be half. So this will be complex 2n, and this will be complex n, and the fibers will be complex n tori. And with at least a relative polarization, so L to X holomorphic line bundle, which is relatively ample, so such that L restricted to the fibers is ample. So this is a relative polarization. Then the fibers are indeed abelian varieties, and you are indeed in the previous example. So this is an algebraic integrable system, what you would call, sorry, fibration here I mean really submersion. So the no singular fibers whatsoever in this assumption yet. So I will allow them later. So if you have a holomorphic torus submersion and Lagrangian with this relative polarization, then this pi is again an algebraic integrable system. And more interestingly, the base admits a special Kähler metric, so or structure, and M admits a special Kähler. So these two bullet points are basically one the reverse of the other. So if you have a special Kähler manifold, you can construct, I mean, assuming you have this lattice bundle, flat lattice bundle, you construct a hyperkähler which lies above with torus fibers. Conversely, if you have a hyperkähler with which fibers, with the Lagrangian torus fibers over the base is special Kähler. It's a two-way construction. However, what's not satisfying for me is that X and M are probably non-compact here, otherwise it's somehow not interesting, and there are no singular fibers, everything is submersion. So my main interest is in the globalized version of this picture where there have to be singular fibers. Okay, so this is just an introduction / motivation. So basically the upshot to take away is that these algebraic integrable systems, the total space is hyperkähler and the base is special Kähler. So, and this is a two-directional correspondence for these things. So my main interest in this is, you can say, algebraic integrable systems with singular fibers and with compact total space. So main interest for this talk is X compact hyperkähler. So really, I should, maybe I can specify more precisely what I mean. So in some sense, I actually mean something called irreducible holomorphic symplectic. So let me write it down and explain why it's okay to call it hyperkähler still. So really, I want to say irreducible holomorphic symplectic. So which means, well, X should be a compact Kähler manifold. And it should have a fundamental group 0, so simply connected now, which probably was not the case before. And with a holomorphic symplectic 2 form, so holomorphic symplectic 2 form, let's say big omega, and such that if you look at the space of all holomorphic 2 form, this is one-dimensional. It's spanned by omega. So it's a whatever. Just write like this. So the space of holomorphic 2 forms is one-dimensional, just constant multiples of this symplectic 1. So that's the definition of this irreducible holomorphic symplectic. And why it's called hyperkähler, it's thanks to the theorem of Yau. So Yau's theorem from the 70s. If you have, so X as such, let's say irreducible holomorphic symplectic, By the way, the fact that you have a holomorphic 2 form already implies that the complex dimension is even. So the complex dimension of X must be even. Let's call it 2n. Yes, so if you have a 2n dimensional holomorphic symplectic and fix any Kähler form you want, omega Kähler on X, then there exists a unique one, omega tilde, such that, I mean, also Kähler metric, such that the cohomology classes are the same, and omega tilde has zero Ricci curvature, so I didn't really define it, but in fact this is the same, in this case, is the same as saying that the holonomy of the corresponding Riemannian metric is equal to SPN, and this again implies there is hyperkähler in the previous sense, so G tilde is hyperkähler, namely, so there was one complex structure which here was not even named. You can call it I if you want, the one that you start with, and you can find two other, J and K, which satisfy the quaternionic relations, and G tilde is Kähler not only with respect to I, which is already written here, but also with respect to J and K. So the same picture as before. Okay, so upshot is on these irreducible holomorphic symplectic manifolds, you can find plenty of hyperkähler metrics. By Yao, in fact, there is precisely as many as there are cohomology classes of Kähler metrics. So fix your favorite Kähler metric and take the class. This class is in H2 or H11, say, with real coefficients. And there is a unique hyperkähler representative. And this H11 can be quite large. Why not? So you can find quite a lot of hyperkähler metrics on this manifold, which now the manifold is compact, so these hyperkähler metrics are usually not explicit. This is obtained by solving a PDE. And the standard example would be to take X, K3 surface. So K3 indeed is a complex 2-dimension. That's the smallest example here, simply connected indeed, and they have a holomorphic non-degenerate 2 form, and by this theorem they admit hyperkähler metrics, which are not known in closed form yet, as far as I know, although some people are trying to find them in closed form, but nevertheless they exist by solving this PDE. I'm not writing the PDE, it's not relevant for the talk, but all right, so.
What would it even mean to write something in closed form?
Yeah, so let's say if your X is a, I don't know, hypersurface in projective space, like that. So if your manifold is very, very explicit, yeah, but in general, you're right, it makes no sense, therefore. Yeah, so I think people are actually trying, like people like Ayotto, Moore, Nitsky, and so forth. So they have some, and maybe Yu Shenlin tried also, but I don't exactly know the status. So there's supposed to be some more or less closed form conjecture. In any case, you can also construct very nice approximations of these metrics by some gluing techniques in some cases. So you can actually understand these metrics much better on certain manifolds. But in general, they just exist by this PDE theorem. All right, so so that's the hyperkähler. So this will be the replacement for my X before, which was T star M mod lambda. Now I want the replacement for pi to M. That's also a well-known object. So this, again, you can call algebraic integrable systems as well. So in fact, this whole story, I believe, was first studied seriously by Matsushita, also around 99, and then many other people since then. So namely, suppose your X, so I'm just going to call X hyperkähler instead of irreducible holomorphic symplectic. It's going to be interchangeable words by some abuse of notation. So when I say X hyperkähler, I guess it's irreducible holomorphic symplectic, but I don't specify a specific hyperkähler metric. Hopefully it's not too bad. So suppose that X is hyperkähler, so 2n and compact. So like in this theorem. And suppose that I have a map. So with a holomorphic map, the F I'm gonna keep the same notation as before, x to m. Oh no, sorry, shoot, it was called pi. Okay, sorry, I call it f now. But yes, almost the same notation, yes. And assume that this one is surjective, so surjective, let's say with connected fibers. And what is M? M in general, it should be just an analytic space, but I'm going to assume that it's smooth, at least for the purpose of this talk. So where M is a hyperkähler manifold also. And I'm going to assume that M is not a point, and M is strictly lower dimensional. So map to a point, not so interesting. Map to something of the same dimension would be interesting, but you would not want to call that Lagrangian torus fibration. So I will rule those out. Yes. These are only the assumptions. Yes. Then stuff follows.
But you don't want any flatness, right?
No assumption. Yes. So then. But in fact, a posteriori will be true, in fact. A posteriori is true, but yeah, not a priori, yeah. And also, I'm assuming smoothness here. That's going to be another sticking point, but I'm going to ignore it. Then, okay, what he shows is the dimension of M is actually equal to half. So M must be half dimensional. And there is a discriminant locus, right? So there exists some, say, the D in M. Closed Zariski closed set, so proper closed analytic subvariety, closed analytic subvariety. In fact, a posteriori it has to be of pure codimension 1, in fact, so it has to be a union of hypersurfaces, but nevertheless doesn't matter, such that the preimage is also closed analytic subvariety upstairs. So. And if you remove those, so from x slash s to m slash d, this is indeed what is called algebraic integrable system as before. Namely, is proper holomorphic submersion. So holomorphic submersion, proper means the fibers are compact, and the fibers are abelian varieties. So with fibers, abelian varieties of the correct dimension, of course. Dimension n, the same as the dimension of the base. So, and Lagrangian, sorry. So the holomorphic symplectic form on X, big omega, restricted to the fibers is 0. So omega restricted to. Right, so this is exactly an algebraic integrable system, but away from this S, you can think of as the singular fibers. D, you can think of as a discriminant locus. That's why it's called D. And away from those bad sets, it's an algebraic integrable system. So i.e. F restricted to X slash S is an algebraic integrable system exactly as before. Or almost exactly, okay. So I did not assume the existence of a relative polarization, which may not exist, but it exists actually locally on the base. So if you take any sufficiently small ball in here, it turns out that you can find a relative polarization on the preimage. It's not obvious, but that's what gives this abelian variety property. That's a clairvoyance result. So yes, it's not a very complicated one, but yes, you need some non-trivial observation for that. So basically, F is a locally projective morphism, but locally in the analytic topology on the base. All right, so a lot of stuff happens, and I mean, maybe let's do some examples, but the point is, of course, now upstairs I have a hyperkähler metric, here I have an algebraic integrable system, conclusion is M slash D carries a special Kähler matrix. That's the important point. And again, likely it's not going to be complete, yeah, okay, and the picture, I mean, maybe the picture you can keep in mind would be to take xk3 with an elliptic fibration. That would be exactly this one here. Fibration f from x to, in that case, would be to p1. And the picture then is, here is your k3, here is p1, and the generic fibers are some nice tori. And then there's a discriminant locus here, just a finite collection of points, right? And then the fibers here are singular. So could be this one or something different, yes. And that's also the picture in general that I just draw. So even if it's not a K3, it's not P1, it's gonna be the same picture because I can't draw anything better. And a very nice result of Yun-Mook Huang, this I think 08, is that in this case actually M is Pn. So it's isomorphic to projective space of half dimension. I'm cheating because, not really cheating, it's all correct, but the point is we're assuming that M is a manifold smooth. And it's conjectured to be true even if you don't a priori assume that it's a manifold. So conjecturally also true if M not assumed to be smooth. So in fact, one can prove that M has to be automatically a projective variety, normal, and even KLT, Fano, Picard number 1. There are many, many properties that this M must have, but we don't know that it's smooth in general. And it's conjectured to be smooth, and therefore Pn. But maybe the conjecture is false. I'm not completely convinced, to be honest. It's just very hard to find examples of these things. And it's known for for n less or equal to 2. So by work of several people. All right, so.
What else? So what could it be? Like a quotient?
Yeah, some quotient, yes. It's definitely expected to be a quotient, have quotient singularities. So if it's not smooth, some quotient singularity. I think there are examples where X is singular and the base has quotient singularities. But yeah, other than that, don't know. I think there were some recent papers where they rule out isolated quotient singularity. So they shouldn't be isolated. Okay, whatever. Yes, it's in some sense going in the right direction, but still. All right, so the base should be projective space. In our talk, it is. And upstairs, you have some hyperkähler manifold. And remark, or many remarks, 2 remarks. So one remark is that if you have this setting, so given such F, remember that X is hyperkähler, so it has not only the complex structure, which is not being written, is called I, let's say, but it has also J and K. So if you switch to K, then this fibration becomes a special Lagrangian. So such F, if I somehow rotate to K, the same map becomes a special Lagrangian torus fibration. So F is a slag torus fibration. And these are the ones that are very important in SYZ mirror symmetry, so Stramiller-Yau-Zaslov. So this is a cheap source of SYZ fibrations by, well, not so cheap. You need to pay the price of finding a compact hyperkähler and then constructing this holomorphic Lagrangian fibration, to which the next remark would help, hopefully. But after you do that, if you change the complex structure, that same fibration is special Lagrangian. Easy way to get a lot of special Lagrangian tori. But sadly, it's not going to work for Calabi-Yau threefolds, because this only works in even complex dimension. So all right. And also conjecturally, so this is a conjecture of, I actually don't quite know, several people, Bogomolov, Hasset, Schinkel, Savon, God knows, Heubrechts, many people. So if X is a hyperkähler, and maybe let's say projective, I don't quite know if the conjecture is made in without that, I have no idea, then X admits such an F, if and only if, so such an F, by the way, is going to be called, I don't know, algebraic integrable system with singularities, or holomorphic Lagrangian torus fibration, where fibration is singularities. Anyway, you can find it if and only if you can find a holomorphic line bundle L over X, bundle, which is an F. So the intersection with all curves is non-negative, and the first-chain class is not the 0 class, but when I integrate the first-chain class to the top power, which is 2n, I get 0. So for K3 surfaces, this is a well-known theorem. You need to find, in fact, for K3 surfaces, you don't even need an F, but here you do, and you just need a line bundle which is not numerically trivial, but the square is 0 on the K3. This is open in general. I think it's even open for Calabi-Yau fourfolds, but I'm sorry, hyperkähler fourfolds. But there was some recent progress, but I still don't think they solved it in general for fourfolds. So in any case, presumably there is some algebraic geometry way to construct these fibrations if you can find these line bundles, which is much easier, and then believe this conjecture. So, all right, and now comes the main point. Of course, time is ticking, so I told you that I would give some introduction and mention the actual results later. So the point came from this famous paper of Gross-Wilson in 2000. So the question is the following. So you have, assume you have this, again, we can say the basis Pn. So this is, you have this fibration with singular fibers, and we know that the total space is hyperkähler. In fact, it has quite a few hyperkähler metrics, one in each cohomology class. And here on M/D, you have a special Kähler structure. So how are they related? And that's the title under this collapsing. So Gross-Wilson, they studied the case of K3. So they took X, K3, F, elliptic fibration. And with the simplest type of singular fibers, so with the S should be 24 of this torus with a pinch. That's the generic type of singular fiber, or the simplest one. And then what they did, they proposed to do the following. Let's pull back the Fubini's 2D metric. I'm just going to call it omega P1, just the Fubini's 2D metric on P1, and add some epsilon, maybe just call it T, times some Kähler metric upstairs. So your omega P1 is some Kähler metric on P1, like Fubini's 2D. Omega X is some Kähler metric upstairs, your favorite one. So in this now for all T positive, this class is actually Kähler, because this is a Kähler class, and you're adding something semi-positive, and this is still positive. And so by Yau, there is a unique omega T hyperkähler in that class. So it's uniquely determined by Yau. And now what you want to do is you let T go to 0, and let T go down to 0. And the point is, if you compute, because the cohomology class of omega T is known, you can check that the volume of the torus fibers is shrinking to 0, like T to the dimension of the fibers. So this omega T are hyperkähler and shrink the volume of the torus fibers. So you're taking this picture and making the fibers smaller and smaller, still over P1, so smaller, 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 smaller. And what you expect to see, then the naive guess is that the fibers disappear, and you obtain some limit which is something on P1. And what you expect then is that the limit should be the special Kähler metric on P1. I mean, that's the only reasonable guess. So, all right, so maybe I don't tell you what they prove, so let's do this in general. So without saying the theorem will be the same as the main theorem. So we're going to do this. So without saying what they proved, I'm going to do this for arbitrary dimensions, for any x compa hyperkähler, and f as above. I mean, to Pn, really. This is m as above. So take hyperkähler with this map, and take, again, omega Pn, omega x, two Kähler metrics of your choice. And then for T positive, let, again, omega T, the same exact construction, be the unique hyperkähler metric. So the same discussion says that the torus fibers, again, are shrinking. And then the theorem is what happens to these metrics. So this is with Gross and Zhang. So as T goes to 0, what you have is that omega T will converge smoothly away from the singular fibers to the pullback of a special Kähler metric downstairs. So this is special Kähler. a special Kähler on P1 minus the discriminant locus, right? Pn, sorry, on Pn minus the discriminant locus. And in fact, this is basically unique because Pn, the cohomology is one-dimensional. So the special Kähler metric is actually unique up to scaling. So you don't need to worry which one, really. I mean, it's the one cohomologous to this one that you picked. I mean, okay, it's not defined on D, but whatever. It extends as occurrence. It has a cohomology class. So anyway, there is basically a canonical special Kähler metric in this picture. And when the fibers shrink, what's left from hyperkähler is special Kähler. And so this was obvious in the original picture, the T star M, because everything was exact, the explicit solution. Here it's not obvious at all, because these ones come from a PDE, which has nothing to do with the special Kähler property. So you can imagine it's believable, but it's not clear at all. And also, what the C-infinity lock means, it just means that when you take the difference of these two, there are two forms upstairs, you treat them as tensors and measure the derivatives with respect to some fixed metric. So this difference goes to 0 together with all covariant derivatives with respect to some fixed metric. So I'm not employing any weird diffeomorphisms here to change stuff. It's the plain smooth topology.
But you don't change the metric as T is going to 0 for measuring the difference.
No. Well, okay. Yes and no, yes.
Taking a diffeomorphism.
Yeah. So if you take a diffeomorphism, actually, some things are easier to prove. So you can stretch out, make it look longer and longer, and it becomes easier. This is actually in some sense, a harder result. But yeah, so if you want the diffeomorphism with the one you would imagine stretching the base, you can also prove it, and it's supposed to be easier. And that's only the first part. And also, in fact, omega t, or maybe gt, the corresponding Riemannian metrics, have uniformly bounded curvature, Riemann curvature, but only away from S, so on compact subsets of X/S. So as long as you stay away from the singular fibers, you have collapsing with locally bounded curvature. This is the best possible scenario. And also, although the omega t's have no reason to be semi-flat, so when you restrict omega t to a smooth torus fiber, you could ask, is it flat? Usually not at all, actually, but asymptotically they are. So what does that mean? If you pick, for the simplest thing would be to say if you pick any point in this Pn minus D and take the fiber, I don't know, let's call X sub y the fiber, then if I take omega t and restrict to the fiber, that's not interesting. Well, it's actually shrinking to 0, but if I divide by t, now you can see that the cohomology class of this metric is fixed, right? If I restrict to a fiber, this disappears, this t omega x restriction, so if I divide by t, it's in a fixed class, so it has a fixed volume, and this then has a chance to say something non-trivial, and this converges smoothly to the unique flat metric on the torus in the correct cohomology class to the flat metric on this torus in the cohomology class of omega x. So these Ricci filamenti are collapsing, but if you rescale by 1 over t, they become asymptotically semi-flat, away from the singular fibers.
Does it have some weaker flatness condition even before taking the limit?
Before, you mean?
Yeah.
I don't know. I mean, this one here should not be identically flat, right?
Yeah.
We should not. You want to say the rate of convergence? I mean, somehow it's getting closer and closer to the flat metric. It's not exactly flat. I think maybe you can specify the rate, like how far is it? But yeah, in general, it should not be flat. I don't think so, yes. I think probably one can even prove it. I have to think a little bit. But the only case when that would happen identically would be if it's a torus, fibering over another torus by the product of tori. Then it would be true. But I think otherwise, probably one can try to prove the theorem that cannot happen if you have singular fibers. Yeah, that's probably interesting. And so in other words, what you can think of is that omega t looks like the pullback of a special Kähler plus the t times this, let's call it semi-flat I didn't really define this object, but you can actually define this semi-flat object, which puts together all these fiber by fiber, and then there are some higher order terms. So this is not precise, but in fact, you can make it super precise. What you can say is these higher order terms, in fact, decay faster than any polynomial in T. So decay faster than T to the n for any n. And there's a small caveat that you may need to subtract here some kind of zero order Fourier mode. So there is some fiber integration part which lives on the base, which you should pull out of here and put it somewhere here, and it goes to zero, but maybe not so fast. And then the leftover is expected to decay exponentially fast, but we can't prove it. But it definitely decays faster than all polynomials. And there is a similar picture in the case of Hitchin moduli spaces, where it's known to decay exponentially fast. And here we don't know it, so we just have this better than polynomial. And the last, I guess, theorem, so I guess I won't have time to mention the stuff with Yang Li, or maybe just one sentence at the end. But the last theorem which I have time to mention with the Yu-Guang, sorry, I've erased the theorem. So anyway, basically you have hyperkähler collapse to this special Kähler on the base, and the first order correction term is semi-flat, so like this. And the last theorem is what happens to the metric completion of the special Kähler metric. So let ZD be this metric completion of this, let's say, Pn minus D with a special Kähler metric. Maybe just use the Riemannian metric so it's not totally ridiculous. So this is a Riemannian manifold. You treat it as a metric space. It's probably incomplete. If it's incomplete, take the completion. You get a metric space, and in fact, it's compact. Not totally obvious. Then the theorem is that then this Z is actually homomorphic to Pn. So this metric completion is compact. It is Pn, and the whole, maybe let's use the metric GT, converges to this metric space in this Gromov-Hausdorff topology. So Gromov-Hausdorff, it's a very weak notion of convergence of metric spaces. So you view this manifold as a metric space, you throw away all the structure, just view it as a metric space, then it converges to the metric space in the only meaningful sense of called Gromov-Hausdorff. And also for the aficionados, I can also mention that what you need to add to the completion has a high codimension. So Z minus the original stuff. So like, when you perform the completion, you need to add these limits of Cauchy sequences. So this is what you need to add. This has a Hausdorff codimension at least 2. So this is the real Hausdorff codimension. Okay, so it's a more technical statement, but by abstract nonsense, you would expect codimension 1, but in fact it's codimension 2. And all of the above is proved by Gross-Wilson in the special case that I mentioned earlier. So proved by Gross-Wilson for X, K3, blah, 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 and 24 singular fibers. But that's done by a totally different method, which was a gluing technique. Our methods have no gluing whatsoever. Our methods are just brutal a priori estimates for the solution of the Yau PDE. So go back to the Yau PDE that I never wrote, prove brutal a priori estimates away from the singular fibers, identify the limit, and then prove some estimates for the asymptotic behavior of this near this D. And here, in fact, the Hodge theory of this periods of the abelian variety fibers enters crucially. So you need to use stuff like Schmidt's nilpotent orbit theorem to get the asymptotic behavior of this near D. And that's needed to get the symmetric completion stuff. All right. In 1 second, I will mention that the stuff with Yang Li that I'm not mentioning was a new proof of the Huang's theorem using the special Kähler metric, at least a new proof of some percentage of Huang. So there is some final step which we can't do with our method, and we have to use Huang's original method, but some other part we do in a different way using special Kähler. Yes, okay, I think time to stop. Yes. Thanks for the attention.
Any questions?
So if in the previous theorem, you didn't know that the base was Pn.
Yeah, you don't have to know it, yes. You don't have to know it. So if you don't know that the base is Pn, I mean, then it's still everything the same, and then here it would be homeomorphic to the base.
But you need to know that it's phenotype or something.
No, I mean, for these theorems, nothing. So even if the base is singular, it's still homeomorphic to the base. So even if it was singular, it would still be homeomorphic.
But I'm wondering about your constructional metric. You were pulling back something that you wanted to be semi-positive.
Oh, you mean the...
And adding, like...
Which one? You mean this disaster here? Yeah, so, or Pn. Yeah, so the point is, if the base is singular, you need the Kähler metric in the sense of analytic space. So, in local embeddings, in some affine space, it's the restriction of a smooth Kähler metric, and those, when you pull back, they're actually smooth upstairs, even at the discriminant. Yeah, but that's not going to be the special Kähler. A special Kähler is not smooth at the singularities. So yeah, so this is just some reference. You can always find it even if the base is singular. Yeah, but yeah, okay, for convenience, I just wrote Pn because we know that it's Pn, but yeah. So we were trying with Yang to prove that it's Pn with these methods, and we almost succeeded, but in fact, there is a glitch in the last.
What's the characterization of Pn?
Yeah, we use Mori theory, this Chomia-Oka Shepherd-Baron, yes. Yeah, with rational curves, and the anti-canonical degree is large. Yeah. So it's with rational curves not containing D. So if D was empty, it would be just Mori's paper. Yeah. So that we have to use that. Unfortunately, we don't have a smarter way to characterize Pn. Yes. Yeah.
So differential geometric analog of the ampleness of the tangent bundle.
No, we tried. I mean, I think it makes sense. You can ask, say, positive curvature away from this D and some extra properties, something not too unreasonable, which are true here. For example, the special Kähler actually dominates some fixed. There's a score. Oh my God. The special Kähler, even though it degenerates, it's always uniformly positive. So you can add this as an assumption, which is very much needed for us, and we prove it in this theorem. We prove this one. So then you can conjecture that if something if you have a compact Kähler manifold with a divisor, let's say, and the metric on the complement has positive bisectional curvature without a strict lower bound, just positive, and this, then it should be Pn. And this we can prove using Mori theory, so plus some arguments, we can prove it. So it's true. But we don't have a proof without Mori theory. Yeah. So this would be reasonable, actually. Yeah. The other glitch is that in this stuff with Yang Li, in fact, you don't have strictly positive bisectional. I mentioned earlier, you have non-negative bisectional. That's not enough to conclude. So unfortunately, that paper is I can't describe it in 1 second, but you need a lot of work. Yeah.
So if you know your total space is Ricci flat.
Yeah. Total space Ricci flat.
Holomorphic fibration.
Yeah.
You could say the base has positive.
Yeah. In some sense, the smooth. So where it's a submersion, what you will get is a metric with non-negative Ricci. Yes. Yeah. So on the base, away from this D, you have in some sense non-negative Ricci curvature. There is some metric with non-negative Ricci. It could be zero if there's.
The metric you have is not complete on the base, right?
Yeah, not complete. Yes, this.
Singularity along
D. In fact.
But that doesn't tell you much about the topology of the base, right?
No, it's not good enough. But what we can say is we actually know the asymptotic behavior quite precisely of this special Kähler near D. We had to suffer a great deal because we needed it very much. So this one here basically has conical singularities along D. D may have several components. It has basically conical singularities up to some small logarithmic error. So it looks like a conical metric along D. But where the branches cross, it's not really conical.
You mentioned one. Can you get on higher genus curves? You can have such metric. Like, can you have such metric on genus 2 Riemann surface?
You mean with the punctures?
Yeah.
With punctures?
Which has like positive curvature, but also has conical singularity along points.
Yes, I think so. But you need to allow this cone angle to be maybe very large. So
But I mean, you don't expect that you would have like a Clavier, say, threefold
No, no.
fibered over.
No.
I mean, you know that it would.
Yeah. So here, the cone angles, I didn't say it, but they're between 0 and 2 pi, so they're in the good range. So if you have that, I think on higher genus, that should not exist, right?
That's correct.
Yeah.
But what is the analog of that in higher dimensions?
Oh, yeah.
Let's say you have a Clavier fourfold
Right.
fibered over a 4 manifold, like a real four, like a complex. And you want to say the base has to be,
Yeah.
I don't know, like say S4.
No. So I mean, in these theorems, the fibration is always holomorphic for me.
Correct.
So the base must be complex.
That is correct.
So S4, no chance. But in some sense, it wants to have anti-canonical semi-positive, the base. It's not literally true because there's this divisor, or in fact, it may not even be a divisor. You have this D discriminant locus messing with you. So
what would be the choice of base for you in that dimension?
sorry, what would
So
be
in complex dimension to base, what would be the correct choice of base?
correct choice? I mean, I think, I don't know a precise classification. Did you not study this? I don't know, but
It could be a few different things.
it could be a few different things. Yeah,
Negative, like PMs, or it could be
yeah, P1 times P1.
dimension 0.
Yeah.
It can be what?
Like both kind of, for me it's negative, for you guys it's positive, right?
Yes. So Kx is negative. Minus Kx is positive. Kx is negative. Yes.
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 Like PM are like flat, right?
Yeah. I think for surfaces, for Calabi-Yau fourfold, what are the possible bases? I don't know if people really classified it. Maybe a bit hard. I don't know. Yeah, it's a good question. I haven't really thought about it. For Calabi-Yau. For hyperkähler, I mean, it has to be half-dimensional projective space, modulo that conjecture, but for...
I think that's all you know, right? It's
Yeah.
just the dimension 0 or minus.
Yeah.
That's
And then maybe they can all happen. Because at dimension 0, I mean, like base Calabi-Yau can definitely happen by some stupid product.
Yeah, exactly.
And the other ones, I don't know.
It would be reducible, no?
Yeah. So my Calabi-Yau was a liberal definition. Sorry. Yes, it would not be strict Calabi-Yau. Yes. If it's strict Calabi-Yau, you get some more restrictions. Yes.
I mean, you could multiply your examples by S1 if you wanted to just get, yeah, but I understand.
Yeah. No, I think the question makes sense, but not sure if people have really looked at it too much. Yeah, I'm more of a metric guy or PDE, so I want to know the behavior of the metrics.
Problem, that's what I'm asking. So if what I thought about is that if you have a G2 manifold with K3 fibration, what are
Possible base.
for the base?
Yeah. Yes, I definitely don't know the answer. Yes, I mean here too, because we proved that this Z is homeomorphic to the base. We were dreaming that maybe we can understand the Z from some differential geometry and prove that it must be Pn. But of course, it's not good enough. Just knowing there is a kind of Gromov-Hausdorff limit of Calabi-Yau tells you very little. So it's not very good.
I think there is like something like a conjecture of Donaldson. I don't know if it's really a conjecture or just thought for a second. But something like in the G2 case, you expect, aside from S3, you expect lens spaces to appear as like the base of
I see.
G2 manifold.
I see. But does he have examples? We don't know. Yes.
Is there any other questions? Any question online? Josh, do you have any?
More about the singularity of GSK near D. What kind of D can we expect, and what is a conical singularity?
Yeah. So. Yeah. I cheated, so I can say more precisely. The point is, in this setting, it was proved by, I think, I forgot, maybe Huang or Oguizo, I can't remember. This D is a union of hypersurfaces. So it's let's say you can write it like this, where these are irreducible analytic, in fact, algebraic hypersurfaces. But indeed, they don't have to be smooth. And they don't have to intersect in normal crossings, so it's just some divisor, right? So just a divisor, and so these various D's should look something like this. Maybe they touch like this. All right, disaster. Now what we actually do is, of course, take a log resolution. So you blow up this base M tilde, to make it a simple normal crossing divisor, yes, so you must blow up the base, and then when you, so I don't know, pi is okay, right? And then when you pull back this special Kähler upstairs after these many blow-ups, now the notion of conical actually makes sense because you have simple normal crossings. I think at least there is a meaningful notion on each component. I think there's also a notion at the intersection. So this conical makes sense, meaning that it's quasi-isometric. It's not true anymore, actually, because of the blow-ups. But the lie would be that this is bounded above and below by constants times the cone model. So the cone model, where you have k of them intersecting, is going to look like summation of whatever dzi wedge dzi bar over zi to the 2, 1 minus alpha I or something like that. So I from say 1 to k, and then plus the Euclidean in the remaining ones, right? Yeah, so this is the kind of model conical metric with some cone angles. The cone angles are actually turned out to be rational numbers between 0 and 1. I mean, these alpha i's are between 0 and 1. And here you want to put the same. Sorry, I didn't write it, but it's supposed to be quasi-isometric. This is, of course, not true at all if you really need to blow up. It's false because you have introduced some degeneracy along the exceptional locus of the blow up, so it's not true. It's true downstairs for sure if you don't need to blow up. If it's already simple normal crossing, then it's actually correct. And otherwise, it's still not true. It's not really conical. There's something like log z to some power, like minus log z to some power, zi's. So you have some conical error. And then, sorry, logarithmic error, and also there is an error from the Jacobian of pi. So you need to insert here the Jacobian of pi, which can vanish. And then we don't actually have upper and lower matching anymore. So for us, the important one is the upper one. So the upshot is, how to say it? If you blow up to make a simple normal crossing, you can actually understand very precisely the behavior along each component. But then globally, you will, this behavior is conical, but it also has zeros because of the blow-ups. And I mean, of course, since I don't know what the blow-up looks like, I don't fully understand these zeros, so that's stuck. But for us, somehow it was enough to have the upper bound to prove this stuff. Yeah. So, but in general, yeah, I don't know what's the notion of a conical metric on this configuration because no idea, especially near here. Disaster. Yes, disaster. But if you blow up, then Hodge theory will help you a lot, and you can get a super precise understanding upstairs of the behavior of this special Kähler, because, orally speaking, in those special holomorphic coordinates, the coefficients are those imaginary part of z, the periods of the tori, and then the periods degenerate. That's understood from Hodge theory, so you can see exactly how the periods are degenerating. As I said, go to Schmidt or whatever, Griffiths, those people, and you get a perfect asymptotic expansion for these periods. So anyway, that's the vague. So it's spelled out in this paper with Zhang, something collapsing hyperkähler in the title from some years ago. Yeah, but yeah, in general, you do need these blow-ups, and that's actually a problem for some other things. But
okay, is there any other question or any question online?
One quick question.
Max?
oh, someone is.
Wait.
Oh, hey, yeah. Hey, Valentino.
We can't hear. One second.
Okay.
Speak again.
Hi, can you hear me?
Oh, no.
It's not working for us.
Yeah,
Yeah.
is it not working?
I'm not sure.
Sorry.
We're fine. We're going to kill this. It's been causing problems.
Maybe type in the chat. I don't know.
Should I keep talking or?
The laptop itself should have sound.
Yeah, should have sounds.
Uh-huh.
Or maybe your sound is going to another device.
I just killed the Bluetooth to make sure it's not topic.
Kill Bluetooth. Okay. Sorry.
Oh, now you're muted.
Okay, yes.
Okay, can you hear me now?
Yes, I think so, yes.
Okay, sounds good. Okay, yeah. So quick question, Valentino. So this whole setup, of course, is reminiscent of the SYZ picture for mirror symmetry.
Right.
Do you have perhaps in work with Mark any thoughts on how it plays with mirror symmetry?
Yes, you're right. Yes, I avoided mentioning. Yes, that's actually mentioned in the original paper with Mark. I mean, this stuff that I mentioned is a bit old, so it's from some years ago. But the point is, yes, for
Max, you muted the thing.
yeah. So is it okay?
I don't know.
Anyway, yes. So
Well, I can hear you from a distance.
and assume that the line bundle restricted to the fibers gives you a principal polarization, which is an extra assumption. Then formally the K3 should be mirror to itself, so it should be self-mirror, and then you perform a hyperkähler rotation to our setting, and you can at least formally obtain a degenerating family of complex structures with a fixed polarization, and the complex structure degenerates to a large complex structure limit. So the upshot is the Riemannian metric didn't change under this hyperkähler rotation, so whatever we proved still remains true, and it applies therefore to some large complex structure limits of hyperkähler manifolds, but not automatically to all of them. And this will proves conjecture of Kontsevich-Soiberman and Gross-Wilson for these complex structure limits, but only for those that you can rotate to our setting. And in fact, Odaka and his maybe postdoc Oshima, they wrote a whole book expanding on this in the K3 surface case to prove that you can leverage this method to prove this conjecture of Kontsevich-Soiberman and Gross-Wilson for all large complex structure limits of K3. But it takes a substantial work. So it's not enough to just take our theorem and done. You need to do more work. So in higher dimension has not been done at all. Probably extremely hard. Yes.
So the same argument with hyperkähler rotation doesn't apply immediately for your case in higher dimension.
It does not apply immediately to all of them. Yes, exactly. It applies to some, and for those which it applies, I think it's spelled out in our paper with Mark and Yuguang from a long time ago. But then it doesn't give you all of them. Yeah, that was the point of this whole book by Odaka and Oshima. Yes.
Okay, very good.
Okay.
Okay.
All right.
Thanks, Valentino.
Okay, if there's any other question, let's Valentino one more.
Okay, thank you. Thank you all.
Have you stopped the? I will stop it now.
All right. Yes, sorry, is there enough physics?
That's fine.
No, it's fine, okay, good.